All right, so we're going to quickly go over the kinematics equations, and I'm going to do a set of 6 kinematics examples for you. This is just practice. Hopefully you can see where this is going with each problem and how they develop. So first, the equations. Remember the equation for average speed, V average equals d over t, where d stands for total distance and t is total time. And we'll go through some examples in the future, or you'll actually run into multiple examples in the future where you'll use different iterations of this formula. But for now, again, we're just going over the basics. When we talk about velocity, I personally like to use position, where delta x, change in position over time, to differentiate between velocity and speed. On the regions reference table, you will see v bar equals d over t, and d stands for distance or displacement. It's not important for regions purposes, but for AP purposes, we do need to know the difference between changes in distance and changes in position. So I like to use v average equals delta x over t to differentiate velocity from speed. Now, in both cases, you can also say v average equals speed 1 plus speed 2 over 2. This is basically saying the average of two speeds is the average of the speeds. Recall that the definition of acceleration is a change in velocity occurring over time. And remember that it's important that acceleration is really a change in velocity, which could mean a change in either speed or direction or both. Again, not important for us for the most part in this unit. We can simply say acceleration is a change in speed, but it will become important later, particularly in Unit 4, that it's a change in velocity. We could also rewrite this equation to say Vx, which means the speed at some position x, is equal to Vx naught, which is the speed at the starting position, plus AXT. Now, this is the way it's written on the AP reference tables. You can do various shortcuts for this. You can just say something like V equals V naught plus AT. The regions table says VF equals VI plus AT. I'm not really too much of a stickler about this. I like to stay as close to the AP table as possible, but I will generally write something like this. This is kind of my in-between compromise for that equation. Okay, so some equations I have not yet used in this series. An equation for position. Now, this equation, when I write it, should make a lot of sense to you. It says that the position of some object depends on what its initial position was, what its initial speed was at that position, multiplied by the time of travel, plus 1/2 AXT squared. And again, you can drop the x's when you get comfortable with this. I'm going to actually erase this last part and write it a little bit better. T squared. Okay, so notice, let's say you have some object that's at some position here, and it doesn't move at all, right? So its initial position and final position will be exactly the same. Now let's say its initial position is here, and it's initially moving when we right when we start looking at it, it's moving this way with some Vx naught, right? Let's say it goes this way, and let's say that Vx naught is 2 meters per second, and it goes this way for 5 seconds, right? Well, it's going to travel 10 meters. That should make a lot of sense, right? If we're going at 2 meters per second, that means every second we're traveling 2 meters, and we do that for 5 seconds, we're going to have moved 10 meters. If we did not accelerate at all, that means that the acceleration part of this equation is 0, and therefore would move 10 meters. But what if we did accelerate, right? What if not only did we have an initial velocity, let's say we also accelerated? That means in those 5 seconds, we're not only going to go 10 meters, we're going to go farther than that, right? Because we're not only going in that direction, we're also speeding up. But note, what if our acceleration was this way, right? Then we would have initially been going at 2 meters per second, but slowing down. And we would not have gone 10 meters, we're going on less. And in fact, if the acceleration is great enough, we might have turned around and gone the other way. So it's really important to note the effect of acceleration here, but to understand that this is sort of a correction factor, right? Based on whether or not the object is accelerating. The last equation is the timeless equation. And the timeless equation, Vx squared equals Vx naught squared plus 2a delta x. Now, this formula is actually a consequence of the law of conservation of energy. And we don't really have a context for introducing this equation or explaining where it's derived from at this point in time. We can simply use it. You could derive it from the other equations given above as well, and you would see where it comes from. But for now, we can just use it. Now, why do we call it the timeless equation? Well, because note that time is not part of this calculation, right? It's neither given nor asked for in the calculation. So we call it the timeless equation. Sometimes there are different names for it. So in situations where time is not given nor asked for, it's a very convenient formula to use. And again, we can just use it based on the fact that we're given the equation. Okay, so let's look at our first example. So an object is moving with a speed of 4 meters per second, changes its speed to 16 meters per second over a period of 10 seconds. Notice that we were not given velocity, so we can just make an assumption that this object is going in a certain direction at 4 meters per second. It really doesn't matter what that direction is. This unit is called one-dimensional motion. So we're assuming that this object can only, if we pick that it's going to the right, then it's only capable of going right and left. Okay, so it changes its speed to 16 meters per second. And you'll notice that I'm representing these things with arrows. So the arrows are indicative of the magnitude of the quantity, right? So notice I drew my 4 meters per second short and my 16 meters per second long to indicate that it's going faster. Now, there has to have been an acceleration here, right? We're going to call this Vx naught, and we're going to call this Vx. Now, in order for the speed to change like that, there must have been an acceleration, and the acceleration has to have pointed in the same direction as the initial speed. Otherwise, we wouldn't have sped up, right? So there's an acceleration here. And note, we don't know what that acceleration is, but we do know that this occurs over a time period of 10 seconds. So there are a few things we can do here, right? And now, in terms of kinematics, there are essentially 6 different things we can calculate. We can calculate average speed, we can calculate initial speed, we can calculate final speed, we can calculate acceleration, we can calculate change in position or distance, and we can calculate time, right? In this case, we'd be calculating not change in position, but distance, because, and they're not necessarily equal. We'd be calculating distance because we are talking about speed, right? We would not be able to calculate change in position because we don't know what direction things are going in. So it would be D. Okay, so we have the time, 10 seconds. We have the initial velocity, or initial speed, 4 meters per second. We have the final speed, 16 meters per second. Okay, so given these things, I could very easily calculate the average speed, right? The average speed would be the average of these two speeds. So 4 plus 16 divided by 2 4 meter per second plus 16 meter per second over 2, which is 20 over 2, or 10 meters per second. Now, I like using average speed a lot. I think it's a nice, quick way to get to the bottom of things. Some people discourage the use of lots of use of average speed. I like it because it makes things a lot simpler for me. I see that I have an average speed of 10 and a time of 10. This tells me I'm going to go 100 meters, right? Because V average equals D over T. So D equals V average T. So 10 meters per second times 10 seconds gives me a distance of 100 meters. So the only unknown here now is the acceleration. Well, we have various ways to get the acceleration at this point. I could use a few different methods. I could say A equals delta V over T. And that would, remember, that's the final minus the initial. So 16 minus 10 is 6 meters per second over 10 seconds, which would be 6/10 or 0.6 meter per second squared. This would be one way. I could also write Vx equals Vx naught plus AXT. This is essentially exactly the same calculation. I'd be subtracting the two speeds and dividing by time. I could also use the timeless equation. Vx squared equals Vx naught squared plus 2a delta x. Now again, d, the distance would stand in for delta x here. And I could also use the position function, x equals x naught plus Vx naught t plus 1/2 ax t squared. And this would be 0. I could just make my initial position 0. X would be d, right? Remember, if delta x is the change in distance or the change in position, so essentially we're going 100 meters in a straight line. So it would be 100 equals Vx naught, so 4 times 10 plus 1/2 times 0.6, 1/2 times a times 10 squared. And if we go through that whole process, we'll get to acceleration of 0.6 meter per second squared. And you can try that out on your own. Notice that there was no one right way to do this, right? Given that I had these three things, I could actually have used, well, I had to get the, I could have found the acceleration first, right? I could have just used this and gotten the acceleration as 0.6 and then plugged the acceleration here to get the position change or the distance traveled, right? There were multiple paths to the solutions. All right, an object begins from rest and accelerates at a constant rate of 5 meters per second squared for 4 seconds. So some object begins at rest and then accelerates 5 meters per second squared for 4 seconds. Okay, so right away we should be thinking about what this from rest means, right? From rest means that our initial velocity is 0. So this should really start coming together for you at this point, right? Our initial velocity is 0. We accelerate at this rate for 4 seconds. What on earth does that mean, right? So if you accelerated 5 meters per second squared for 4 seconds, if you just go ahead and multiply those two things together, right? Just multiply 5 meters per second squared by 4 seconds, right? What does this give you? Well, this seconds, right? If we look at it as 5 meter per second times seconds times 4 seconds, what's going to happen here is we're going to cancel out a second, and we're going to get 20 meter per second. What is this 20 meter per second? That's the speed, right? That's the speed that this thing's going to have attained when it gets here. It's going to reach the speed of 20 meters per second. And again, this should be making tons of sense without any equations, without having to put things into calculations right away, right? Yeah, I'm busy. So we could put it into a calculation just for the sake of formality. Vx equals Vx naught plus axt. So 0 plus 5 meter per second squared times 4 seconds gives us a final speed of 20 meters per second. Okay, what else could we do? We have our timeless equation, Vx squared equals Vx naught squared plus 2a delta x. At this point, we have the acceleration and we have the two velocities. We could use this to find position. We could also do something else that I really like, which is get the average speed. The average equals d over t. Now, the starting speed is 0 and the final speed is, sorry, not that. The average equals v1 plus v2 over 2. So speed 1 is 0 and speed 2 is 20 meters per second. So we'd have an average speed of 10 meters per second. If our average speed is 10 meters per second, and we're traveling for 4 seconds, that means we're going to have traveled 40 meters. Right? Our distance of travel is 40 meters. So if we look at the various things that we can find out, have we found all of them? So recall, we could find average speed, which we've concluded is 10 meters per second. Initial speed is 0. The final speed, 20 meter per second. The acceleration was given, 5 meter per second squared. The distance traveled, 40 meters. And the time was given, and that is 4 seconds. So again, note there's only 6 things that we can find as part of a 1D kinematics problem. Once we understand that, the game really becomes how do you find them, or how do you find the ones that you're looking for, right? All right, an object moving with a speed of 20 meters per second comes to a stop while slowing down at a rate of 2 meters per second squared. Well, let's stop and think about this for a second, right? So V average, Vx naught, Vx, acceleration, distance, and time. Our acceleration, 2 meters per second squared. Our initial velocity, 20 meters per second, comes to a stop. That tells us our final speed is 0. Now think for a second, right? Well, right away, what might jump out at you? Well, once again, our average speed is going to be 10 meters per second. Why? Well, because we're going from 20 to 0, right? So the average of 20 and 0 is 10 meters per second. How long is this going to take to happen, right? Think about that. Think about what's going on here, right? We have something that's moving at 20 meters per second, and then it loses speed at a rate of 2 meters per second. how long is it going to take for it to lose this 20 meters per second of speed? Well, it's pretty clear to me that it's going to take 10 seconds. It's also clear to me that this object will also travel a distance of 100 meters. Why? Well, because V average equals d over t. Now, let's look at the calculation to get the 10 seconds. Vx equals Vx naught plus axt. 0 equals 20 meter per second plus 2 meter per second squared t. So negative 20 equals 2 t. T equals negative 10 seconds. Wait, now that's a problem, isn't it? Right? This is an issue because we can't have time being a negative quantity. Well, how are we going to reconcile this? Well, think about the fact that acceleration has to have a direction, right? So if this is a speed 20 meters per second, right? So if the objects, we say that it was going this way, right? We're going to have to pick a direction for it. And it's slowing down. That means that the acceleration must have been opposing the velocity, right? Even though this is a speed, we're going to have to pick a direction for it because we need to know if the acceleration was in the same direction or the opposite direction to do these calculations successfully, right? In the previous examples, things were speeding up, so we know the acceleration was pointing in the same way as the initial velocity. Now we have something that's slowing down. So now we know that our acceleration must oppose our velocity. So therefore, if I'm going to call this plus 20 meters per second, I'm going to have to call this negative 2 meters per second squared. And now we can see this solves our problem with our signs. So anytime you come out with time as a negative number, what you want to do is go back and look at the directions of your velocities and accelerations and make sure whether or not they should be facing the same way or opposite ways. I could have just as easily solved this by saying that the initial velocity was pointing in the negative direction and that the acceleration was pointing in the positive direction. And then this negative sign and this positive sign here would have resulted in me dividing a positive by a positive rather than negative by a negative. And again, I'd get a positive result. An object moves at a constant velocity of 10 meters per second west for 30 seconds. Well, what do we get out of this right away? You should immediately, at this point in time, you should immediately right away be saying what, right? What's the one thing that you should immediately say to yourself as soon as you read this? Well, when I read it, I say the object went 300 meters. Why? Well, because the average equals d over t, and d equals v average t. Or actually, more specifically, since I'm talking about velocity, I should be saying v average is delta x over t, and delta x equals v average t. Now, if I say 10 meters per second here and 30 seconds, 300 meters, notice that I need to know the direction if I'm going to talk about the displacement, right? The distance is 300 meters, right? No problem. The change in position, if I'm calling west a negative direction, I'm going to have to call that negative 300 meters, right? It should be negative 10 meters per second. If the v is a speed, I just put it in as 10. If it's a velocity, I put it in as negative 10. The acceleration here, 0, right? So look at what this does to our timeless equation. Vx squared equals Vx naught squared plus 2a delta x. If acceleration is 0, what this tells us is that Vx is equal to Vx naught squared. That is the definition of constant velocity. The definition of constant velocity is 0 acceleration. Look at our position equation, x equals x naught plus Vx naught. Let me fix that up. Vx naught t plus 1/2 axt squared. If acceleration is 0, that's going to get rid of this whole term. If our initial position is 0, look at what happens. This equation essentially degenerates into this equation because Vx naught is V average, and it's equal to Vx, right? They're all the same speed. If the velocity is constant, then all three of these velocities are the same. The initial, final, and average velocities are all the same quantity. All right, two more examples. An object moving east at 14 meters per second changes its velocity at a constant rate and is moving west at 20 meters per second after a period of 34 seconds. So we start out, we're traveling east at 14 meters per second. And then after some period of time, we end up going west at 20 meters per second. And this happens over a period of 34 seconds. All right, so kind of interesting here, kind of complicated. Calculating the distances here is not as straightforward as it seems, okay? Calculating the change in position is fairly straightforward, but calculating the distance traveled isn't as clear, okay? Because we don't know, did this thing travel, it started out traveling east and in the end it's traveling west, right? So how long did it take for it to stop, turn around, and all that stuff? So the best thing to do here, looking at our the average, Vx naught, Vx, A, delta x, and t. T is 34 seconds. Vx naught is plus 14. Vx is negative 20, right? So our best bet here is probably to find the acceleration. This is probably what's going to help us out the most. So Vx equals Vx naught plus axt. Ax equals Vx minus Vx naught over t. So negative 20 meter per second minus 14 meter per second over 34 seconds gives us an acceleration of negative 1 meter per second squared. Now this makes lots and lots of sense, because in order for us to end up with an acceleration in the direction to the west, we're with a velocity to the west, we're going to need an acceleration to the west. So we can kind of map out what happened here, right? How long did it take for this thing to stop and turn around and start going the other way, right? So, well, if it was started at a speed of 14 and it was accelerating at 1, it stopped moving after 14 seconds, right? At 14 seconds, its speed was 0. Okay. Per second squared. And we can talk about what distance it covers in that time, right? So how far does it go in the first 14 seconds of travel? Right? So let's consider how far it goes in the first 14 seconds of travel. So let's say we could do it as an average speed calculation. We could say that the average speed is 7 meters per second and it travels for 14 seconds. So that would mean the first set of travel is 7 meters per second times 14 seconds. So we're going to have 98 meters of travel to the east. Then after it stops, it's going to have traveled to the west for another 20 seconds, right? So 14 to 34 seconds. So we got 20 seconds of travel to the west. And we're starting with a speed of 0. And we're going to accelerate at 1 meter per second squared. So our final speed is going to be 20 meters per second, negative 20, for an average velocity of negative 10 meters per second. And we're doing that for 20 seconds. So our delta x now is negative 200 meters. So our overall change, so our distance traveled is 98 plus 200, or 298 meters. But our change in position is 98 minus 200, which is minus 102 meters. So we're going to end up 102 meters to the west of where we started. Okay. Now we can check and see if this agrees with our position function, and it should. Right. So we should get minus 102 meters from our position function. So x equals x naught plus dx naught t plus half ax t squared. So dx naught, 14 meters per second times 34 seconds plus 1/2 negative 1 meter per second squared times 34 seconds squared. And if we plug this in, and you know what, I'm going to clean this up a little bit because it's looking very rough. Not a whole lot better, but okay. So 14 times 34 is 476 plus 0.5 times negative 1 times 34 squared gives us negative 102 meters. So notice our position function gives us the correct answer regardless of our regardless of the fact that we changed direction and all that, right? So notice this is a position function. It's not a distance function. It doesn't tell you how far you went. It tells you how far you are from where you started, right? Or the position that you end up with relative to whatever x naught is. So very important, right? If you wanted to know the total distance, you would have to have done this as 2 separate calculations. And note that the distance is 298 meters. Right? It is not 102 meters, right? The distance of travel is not 102 meters. It will be a little bit more obvious to us when we do this with the graphs, right? Now, if you were to calculate the average of 14 and negative 20 divided by 2 negative 3 times 34, you also get negative 102, right? So the average velocity of negative 3 meters per second also allows you to calculate the final change in position, right? But in order to calculate the distance, you would look at the average speeds over those two intervals of travel. And I need to, all right. Question 6, an object moving south at 10 meters per second slows down until it's moving south at 2 meters per second while covering a distance of 40 meters. So V average, Vx naught is negative 10 meters per second. I'm calling south my negative direction. Vx is going to be negative 2 meters per second. Again, I'm calling south my negative direction. Acceleration, change in position, and time. Now, change in position and distance are going to be the same thing here because I'm only going in one direction without a change in direction at all in between, right? I'm not stopping and then speeding up in another direction. So I can say that the change in position is not 40 meters, but negative 40 meters. Why? Because this tells me a distance of 40 meters, but I know I was traveling south, right? I was going south at negative 10, and I end up going south at 2. Okay. So I go from negative 10 meters per second to negative 2 meters per second. What does this tell us about the acceleration? Well, if we're going this way, we're going south, and we're slowing down, that means we have to have an acceleration that points to the north, and therefore whatever acceleration we calculate here is going to have to be a positive quantity. I can calculate the average speed. That's pretty easy. It's simply negative 6 meters per second. It's the average of those two velocities, right? I can use this to determine the time, but you know, and again, there are different approaches here that would be completely fine. But let's go ahead and calculate the acceleration. Now, how would you calculate the acceleration? This is a perfect time to break out the timeless equation. Okay. So we have negative 2 meter per second quantity squared is equal to negative 10 meter per second quantity squared plus 2a times negative 40 meters. All right, so we've got 4 equals 100 minus 80a. So 4 minus 100, negative 96. Negative 96 equals negative 80a. So a is going to be 1.2 meter per second squared, and note that it does indeed come out positive. And now we could use pretty much any formula to get the time that we like. The one formula that would not make sense to use at this point, although we could use it, and we will actually look at why it's not particularly a good idea, although we could use it. Let's look at the position function. Let's look at the position function as a way of getting time here. So x equals x naught plus bx naught t plus 1/2 axt squared. So we have that. So we'd say negative 40 equals negative 10t plus 1/2 of 1.2, so 0.6 t squared. So the problem here is that we end up with a quadratic function, 0.6 t squared minus 10t plus 40 equals 0. Now you can do this, right? You can go ahead and solve this as a quadratic. This is certainly not something you can factor, but if you know how to use the quadratic solver, which I can show you how to use in the class, and I will, I'm going to go ahead and use my quadratic solver. So 0.6 x squared minus 10x plus 40 . So I'm getting time equals 6.66 seconds or 6.67 seconds. And so that's my first root, and my other root for this equation is 9.99. Okay, so what is this telling me, right? It's giving me two answers. Two correct answers, right? There's two real roots here. Why on earth would there be two real answers to this problem? Well, think about this. The object is moving south at 10, and it's accelerating north at 1.2, right? So it's going to go south 40 meters, and the first time it passes 40 meters south of where it started, this is going to be 6.66 seconds. But what is eventually going to happen? Eventually, this thing is going to stop, and it's going to start coming back, right? So when it comes back, it's going to pass through this 40-meter south position again, and that time at which that happens is going to be 9.9 seconds. So both of these times are actually real and relevant times. This object will have a position of 40 meters south of its starting point at these two times, right? Now, assuming that it stops and doesn't come back, then this would be the only time at which it occurs, right? But this time is definitely going to happen. This time might happen, right? We're not sure. We're not sure what's going to happen after we pass through the 40 meters. Maybe it'll continue with the same acceleration and come back the other way. And if it does, then if the acceleration stays constant, it will be back at that position at 9.99 seconds. Okay, so I hope these examples have helped you out a little bit. You should be doing this in conjunction with all of your other examples and in conjunction with your classwork and your do-nows. So hopefully, if you're looking for a little more practice or just some clarification, this video has given you some help or some things to think about.